Welcome to the Node Governance podcast, where we discuss all things blockchain, smart contract programming, cryptography, and dark magic. We're in great company today, as I am welcoming Jeremy Bruestle on the show. Jeremy is the CEO of RISC0, a zero-knowledge, verifiable general computing platform based on the RISC-V microarchitecture that makes it easier for mortals to leverage zk probability for their programs in a hopefully seamless fashion. It's really a pleasure to have you here. How are you?
I'm doing great. Thank you. Good to be on the show.
I propose that we start by, I succinctly introduced you, but it would be cool to know a little bit more about your background. What were you doing before? And what led you to work now on RISC0?
Yeah, absolutely. I have been an entrepreneur in a number of different sort of verticals, but the sort of underlying theme is I'm always trying to figure out how to take new mathematical breakthroughs and apply them. Actually, my companies have ranged across mesh networking, bioinformatics, compiler technologies for machine learning. But I started really getting into ZK about 5 or 6 years ago. I basically ran across some papers, and there was this PCP theorem that basically said that it's possible to verify some arbitrarily large amount of computation in constant time. And the idea that this was feasible, it seemed impossible. It blew my mind, right? I was like, how is that even a doable thing? So I started really getting into and trying to understand this, learned all the sort of mathematics behind zkPs. And I realized that they were getting to the point where it was nearly, at the time, it's just a number of years ago, where it was going to approach being practically useful. And it was obvious to me that this would have a big impact on any kind of distributed systems where there's like need to trust another party. And the implications for blockchain were really very clear. So I tried to get my friends, the other co-founders, to like get interested in zkPs, because we had just sold our company to Intel, my previous compiler company, and we were bored at like a large corporation. But I kept trying to sell them on it, and they were like, well, how, like, it's a general purpose programming thing. How do you program? And I'm like, polynomial constraints on some finite field elements, et cetera, circuit, blah, blah, blah. And they were like, no one wants to do that, Bruestle. It's a dumb technology. And so anyway, I kept reading the math papers, kept trying to convince them. They kept being uninterested. And then one time, I think we were all like hanging out, having a beer or whatever. This discussion came up, which is, well, if you can make an arbitrary circuit in a zkP, couldn't you like make a circuit that emulated an existing processor and then just run regular software inside the zero-knowledge proof system? And that was sort of the genesis. The idea was this realization that we could make zero-knowledge proofs run ordinary code. And then the real question was just a matter of like, can you make it fast enough? Can you make it efficient enough? And so, I started prototyping things out. Pretty soon it became clear that it would be feasible. And so that's when we sort of decided to, quit the day jobs and start the company. So
it is funny how a few protocols tend to stem out of beer drinking sessions with the lads, or a few beers and a few coffees late night.
Yes.
And then an idea come out of nowhere. So it seems to be the case of RISC0. I think that Solana was the same. It was 2 coffee and 1 beer, and consensus twist came out of this. I mean, it is very controversial, but that's very interesting to see that it came out of this. So to break it down, RISC-V is, let's say, a processor architecture. You're fitting it into a zk circuit, sticking it into a circuit, and then you can write arbitrary programs that target that match with these specs, and it'll make them provable. Am I getting this right?
Yeah.
Okay.
Yeah, I mean, and we picked RISC-V in particular because we wanted something that there was already good compiler tool chains for, already good infrastructure for, something that was like used a lot in the real world. But the other real options included like MIPS or ARM or x86. I mean, obviously x86 would be great if we could make an x86 zkVM. But the reality is those processors, the ISAs, for those are extraordinarily complicated. And RISC-V in particular, was designed with sort of maximal simplicity in mind. And it's very modern. There's a ton of open source support for it. It's a very open, sort of platform. And we looked, and, there was good compiler tool chains for most every language. Actually, one missing one, unfortunately, is we looked at Go. Go does have RISC-V support, but actually only for the 64-bit version, not the 32-bit version. But we are going to eventually work on fix that as well. But yeah, so that was basically the reason we picked that instruction set. And I think one thing it's very easy to underestimate the power of existing development ecosystems, right? I think a lot of the zk projects have built their own custom DSLs or their own, architectures. And the reality is that it takes a long time for an ecosystem to build up all of the standard things you need to build software, right? All of the different libraries, all of the different, support. And so picking something where we can use existing off-the-shelf libraries was a huge, huge win for us.
You take advantage of all these network effects, communities, tooling, you name it.
Absolutely, absolutely. I mean, I think the other option, obvious option was the EVM, right? And we've seen a number of the zkEVM projects where they basically implement the EVM directly as a circuit. And I think that the one major disadvantage of that technique is that the EVM is a very complex beast as well. I mean, it may not be quite as bad as like Intel's architecture, but it's still, complex. And I think the real demonstration that the approach of picking a very minimalist architecture was really sort of shown when we introduced zeth, which basically allowed us to, instead of making a circuit that emulated a EVM, we instead just took and compiled an EVM VM from a RETH, our EVM project, into RISC-V and then ran it. And actually we were like the first ones with a type 1 zkEVM. And that was because we were just running existing EVM software inside this general purpose zkVM. So yeah, but I think, at this point, a lot of other people have sort of caught on that this is a good idea and are building things that are similar. But I think it was a really, at the time we first sort of started talking about it, it seemed like a little bit of an oddball choice, but I think it was a good choice.
Yeah, I would love us to dive deeper into these experimentations that you guys have done at RISC0. Like there's, of course, the zeth project, that Doom, provable Doom that you shared on socials a few weeks or a few months ago.
Yes.
What you're working on with what I would call like zk fraud proofs, validity fraud, weird way to call them. But yeah, I would love to explore that a little bit further. But now I would like to have an overview of the, let's say, RISC0 stack. So there is a zero knowledge virtual machine.
That's right.
There is Bonsai. I am able as a developer to run your stack locally on my computer to run my experimentations and do whatever I want out of it and generate receipts. But I can also summon proving network to get the job done.
Yep.
Would you care like breaking down these two approaches, these two systems, and all the other components of the stack that I might have missed?
I think so sort of the core technology is this open source zkVM that lets you, hello.
No worries. Please continue, Jeremy.
Oh yeah. So the core, the core is this open source zkVM that lets you run. Really, actually, it's just a normal ELF file that you compile down inside a zero knowledge proof system. And both the prover and the sort of verifier for that are Apache 2, fully open source, including also sort of a lot of the accelerators. So we currently support GPU acceleration and so on as well. And then, on top of that, we have actually a couple of other things which are more like sort of libraries that make this process easier. There's sort of zeth, which is for proving, Ethereum blocks, but we also have Steal, which basically allows you to execute view-only contracts inside the zkVM so that you can prove things about previous Ethereum state, for example, in a very easy way, programmer-friendly. So we're sort of building all these tools to make the Web3 integration story better. One of the main ones, one of the critical ones that we are actually about to, I think in the next 2 weeks, it should be up and running, is this verifier contract on Ethereum that will actually run the verifier on chain, along with sort of we're about to release our 1.0 version of the zkVM, which has been properly audited and we've dotted all the I's, crossed all the T's. We actually believe that version of the zkVM is ready for production. People put money behind it, where we'll put our name on the line that it's ready to go. So we're super excited about that. And then I think, yeah, as you mentioned, the last sort of component is right now the way that you generate a proof is you run the prover. But in a lot of cases, you might not want to run the prover locally on your own machine. And so we have this sort of Bonsai service that lets you sort of get proofs generated, in the cloud, if you will. We are working toward, have not released the details of yet, sort of a more decentralized network for proving. But I think that's still not quite something we're ready to share all the details of, but that is the direction we're moving toward. But yeah, so largely the stack today is these sort of the core zkVM, lots of additional sort of helper libraries and sort of systems, and then the on-chain verifier and the bonsai proving network.
Great stuff. And I just wanted to say that we just got joined by Thor. Thor is our co-host today, polynomial marauder, a stark alchemist, and a good friend, taking up Daniel Lumi's torch for this new season. Thor, how are you? And have you heard about RISC0?
Yeah, I'm doing good. I'm just joining you from my office in California. And the thing that's exciting to me about RISC0 is I think you guys at RISC0 seem to have identified that it's a lot harder to write circuits than it is to write programs. And I think RISC0 was fairly early in understanding that we could actually do a fairly decent amount of compiler engineering and make it a lot easier for developers to write Rust programs and then compile them into a virtual machine of the RISC-V architecture. So that's sort of exciting. I guess like the thing that I'm curious about, there's been a lot of growth in the sort of development of different virtual machine architectures since even the beginning of this year. We've seen like the introduction of the Jolt virtual machine. Succinctive recently introduced their own virtual machine. And there are a couple of other virtual machines that are aiming for different kinds of privacy preserving techniques. All are making slightly different architectural decisions. I'm sort of curious to hear, Jeremy, your perspective on what architectural decisions has RISC0 made as you sort of like tried to answer the problem of like, how do we bring sort of programs to developers, and maybe talk a little bit about like what you're seeing other teams making along that sort of same line.
We were, I think, very early in this notion of using some existing standard ISA. I was just saying earlier that I think this is really important because it lets you access a very wide range of existing, software, which is super helpful. Like I think a good example is, like, you want to prove there's some correctness of some chess move or something in some kind of ZKP. Now you just import a library or parse a JSON file, read an image, like any kind of thing. Even for the more blockchain-focused uses, the fact that we were able to get Zeth, which is our sort of type 1 zkEVM, the original version of that, I think, was 3 people over 3-4 weeks to get that stood up, right? So I think that's sort of the value of using an existing standard. And I think actually, the fact that I think we picked a good choice for that particular choice, which is the RISC-V architecture. I mean, obviously, it certainly helps prove our thesis on that there are 2 other groups using that same exact processor architecture, being Succinct and Jolt, of course. I think that long term it is very likely that we will see this direction of the general purpose ZK moving closer to sort of ordinary non-ZK computing, become increasingly prevalent. I think a lot of it is, I think back to in the early internet, right? When the web first came out and we didn't have HTTPS, we didn't have TLS, there was a lot of things you couldn't do because you're no end-to-end encryption. I'm not going to put my credit card into a website to buy something, right? All these e-commerce use cases were not usable. And so there was this huge push to get end-to-end public key-based encryption and all these things into these types of browsers. But I think that a lot of those technologies, they started as being a big technical advancement, but I think eventually they sort of disappear. Like the difference now is, a single letter on the URL, right? HTTP or HTTPS. And so the sort of revolution of public key cryptography is so completed that it's almost invisible. And we sort of really believe that ZKP, while originally an extremely difficult technology for a developer to apply, we want to make it so easy that it's just like, oh, do I want to run this program normally or in ZK? And so I think we will see a continual convergence of the types of things people do in normal development and ZK development. I do think one interesting thing is I do think we will also see that from a performance perspective, there are still places, particularly the cryptographic operations like cryptographic hashing, signature verification, right, where it's very critical to accelerators for the ZKP, or people call them precompiles often as well, right, in the sort of model of Ethereum. And I think that these sort of ZK precompiles, you'll end up with this world where the vast majority of your code is just normal Rust code or normal C++ code or Go code, and you just run it inside of a zkVM. And then there's a couple of acceleration libraries for specific use cases that are cryptographically heavy. And I think with a combination of this general purpose and these sort of precompiles, that you'll end up in a place where the performance for general purpose ZK is as good as any sort of more of these sort of custom circuit kinds of things, and we'll see that kind of disappear. I mean, we saw that in early silicon, right? Originally, people made a new custom ASIC for every circuit, right? There was a time once when the soda machine had a specific custom ASIC that literally counted quarters and nickels and dimes and determined when they added up to 50 cents in a hard circuit. And of course, the emergence of sort of the microprocessor meant that almost everything that had custom circuitry for it just went to run on a microprocessor. And then there was a couple of special cases. There were cryptographic accelerators or those kinds of things. But yeah, I think that we'll see the same thing with ZK. Sorry, that's a little rambling. Apologies.
No, that's pretty cool. So right now you have that zkVM, which is like emulating a real processor, and this kind of a gap. Are you actually measuring the performance of that VM using megahertz and operations per second? You obviously are, and you're working at reducing the gap between actual hardware and that sort of emulation that you're building. And I believe that's why games like Doom are able to run now, because the first iteration of that game probably ran on a Pentium 1 or something even worse.
Exactly. We're sort of entering, you've been sort of tracking through the eras, we started off in the like early 80s, and we're definitely well into the, 90s. We're sort of moving through the history of computing in terms of the performance. Since the beginning of this year, we have had about a 3x performance improvement across the board for our zkVM in terms of how many megahertz it runs at on a graphics card, on a GPU. We have had support for GPU acceleration for quite a while. We're very focused on that sort of performance story, and we really think that there's quite a lot of room still to go. I think that'll be continually important, because I actually think it's not so much the speed, though, that matters. It's really, in some sense, the cost for different use cases. So if I look at, say, proving an Ethereum block, if it's $100 to prove an Ethereum block, maybe it's useful for certain sort of fraud-proof cases or cases that happen rarely, right? If it's like 10 cents to prove an Ethereum block, why wouldn't you just always do that, right? There's this big type, you start to unlock more and more use cases as the performance gets better.
Yeah, and since we're in blockchain, there's also a question of latency, because if you're making provable, let's say a provable Ethereum type 0, type 1 system, you're bound to the time it takes to generate the proof to offer some sort of finality. I believe that the job at the RISC0 network level or bonsai level is highly parallelized. So it's fragmented in some kind of segments that are handled by operators in the network, and then all put together via recursion, and voila, we have transformed some huge work that records a bunch of cycle into something that's parallelizable. But we're not there yet in regards to having like that kind of real-time result that sometimes we're looking to achieve for financial use cases. So is there a future where we can foresee a system like RISC0, a general purpose zkVM, offering like great performances? And
yeah, absolutely. So if you look at sort of a lot of our decisions, we've always focused very much on the sort of two things, which is this sort of reduction in the cost per megacycle of proving, if you will. Like how much does it cost to prove 1 million cycles of RISC-V execution? And then the second one being the sort of question of how do you maximally parallelize the proving process and make it amenable to parallelism so that you can, go as wide as you need to reduce latency if you want to reduce latency. And I think that, a lot of our design decisions around both the zkVM, the way our memory argument works, a lot of these things are really focused on that. So recently we introduced now have these sort of multiple levels of what we call like execution or pre-flight, right? So at the end of the day, the actual RISC-V program itself has serial execution semantics because it's emulating a real processor that runs in sort of serial. But what we can do is we can emulate that at a very low level of fidelity very, very rapidly, and use that to figure out the memory state, the state of the system at various points in time. And then we can now spin those off to different machines to go fill in the details, and then to the GPU to do the full proving. Actually, we are actually already starting to consider interesting questions like, well, what if you did want to have a multi-threaded execution environment for your programs to be able to have parallelism even at the VM level? But those are all still not in the current version yet, but we're thinking about these matters. So,
and I've read that one of the schemes that you're using to speed up proof generation is a technique called continuations. If you would explain how, so in like normal parallel computation, we need to model that maybe we have like 8 different threads and we're going to run several portions of the computation. Maybe this portion goes on thread 1 up to thread 8. And I want to ask if the analogy from continuations to parallel processing is relatively direct, or if it's actually using a different part of computing some portion of the stack trace of a single threaded program and then combining those proofs in a later.
Yeah, it's more like the latter. So effectively what we do is we run the serial execution without doing the full proving process. So we're doing it in a much faster emulation, but it's still cycle accurate, exact to the semantics of what the proof system eventually requires, because of course, it needs to be exact for it to work. But then what we do is we pick a particular interval, in this case, usually 1,000,000 cycles of execution. And on those sort of 1,000,000 cycle boundaries, we freeze the program, if you will, and we Merkleize the state of memory. And then when we go to the next, so in each of these sort of segments, we then sort of begin by bringing that memory back in, running it for another 1,000,000 segments, and then putting re-Merkleizing the memory, right? So we actually, you can think of it a lot like paging. In fact, we actually call it paging internally, in the sense that you imagine that each of these little segments, often they don't access the entire state of memory, they only access some small portion of memory. So we only sort of do the Merkleization for the pages which are actually hit by the execution. So, and we actually have this like Merkleized structure that looks like a lot like a page table, right? It's actually interesting to me how you sort of feel this like pull of the general purpose ZK more and more toward a lot of these concepts that exist in the rest of computing, but always in a slight strange mirror, funhouse world version, because you can use weird things like non-determinism and stuff in ZKPs, which you can't in the normal world. But yeah, so the theory is you do this very fast serial execution to generate each of these sort of segments, and then each of those can be shipped off to different machines to have the full actual ZKP proving process happen. And the result is a proof that if we begin in memory state X and we run for 1,000,000 cycles, we end in memory state Y. And then we have another proof that says if we begin in memory state Y and we run for 1,000,000 cycles, we end in memory state Z. And then we can use recursion to verify both of those proofs and prove that if we start with X in 2,000,000 cycles, we end in Z. And so by doing that, we can basically chop up a program and then in log n time, using recursion, put all the various pieces back together. That allows us to run very large programs. Not only do we use that, of course, for like Zeth, the Doom thing, we can run we can run something that we could split the work across hundreds of machines if we feel like it. So.
I wanted to expand on, you mentioned that some pieces of code touch some portion of the state, and that you can isolate which pieces of code which touch which portion of the state. And that's already sounding a lot like the way we think about our code when we're thinking about parallelizing it.
Mm-hmm.
So I'm curious, if I were to write parallelizable code, would I be able to think about that in advance as I'm writing the code, and then allow that context to inform how the proof generation step occurs, or if that is something that you're thinking about introducing?
Yeah, absolutely. So in some sense, with a little additional programmer effort, you can sort of do that now, because we also have this feature, which is proof composition, where the user can run program and another program, and then verify both those proofs in a third program, and do that efficiently using the same sort of efficient recursion support that we have. So to the extent that you think of it more like forking to other programs, you can sort of already package up and distribute your proving workflows in that way. We are looking into sort of extending the programming model to make some of these things, again, more like, wherever there's like existing interfaces, whether it's like, POSIX for I/O between the prover and the outside world, or whether it's questions of how would you think about what a file system would look like in a ZK proof, or all of these other kinds of different abstractions that programmers are familiar with. We're always sort of asking the question, what's sort of the next level of compatibility we can bring to the programmers so that ZK looks more similar to what normal programming does, with still maintaining a good degree of performance and making sure that we're following good cryptographic. There's a lot of ways for a programmer to accidentally shoot themselves in the foot when they're writing a ZK program. So we, like, for example, randomness being one of them, right? We actually have some, by default, most of the random number generators in our system are explicitly turned off, and you can turn them back on, but you better understand what kind of randomness you're generating, because like a lot of times people want to use randomness as though it's truly random, but you actually have to think about how that fits in with the blockchain protocols you're using. Or is it deterministic randomness based on a seed? Who knows the seed because they can predict the randomness? Who can control the seed because they can control the randomness, right? So as we sort of go through and try to make things look as much as possible like the the non-ZK world. We also are thinking about where are developers likely to run into surprising behavior and could use like a heads up. Maybe the call refuses to compile until you set a flag in our system, so that they make sure to think about what they're intending for that.
Yeah, that
Yeah.
makes a lot of sense. Go ahead, Sam.
I was very curious. I would love to understand a little bit more what's the cryptography, or how does the proof generation works with the RISC0 zkVM. So by scouting the internet, I understand that it's a multi-layer recursive proving system that we have here. With it's a Fry-based system that gets wrapped into a Graph16 proof. Could you explain these design choices and how these different proving steps compose together?
Yeah, absolutely. So we chose a sort of a more Stark-like or Fry-based system, largely because, especially for systems that repeatedly run the same computation or the same sort of logical circuit over and over again, which of course a VM does. It's more or less making a state transition function for the processor over and over again. Fry-based, Stark-based kinds of proof systems have a much better concrete performance numbers than, say some elliptic curve snark type stuff. And so we really chose that primarily for just proving speed sort of reasons. And the verifier speeds are very good as well. The disadvantage, the downside those types of systems have is the size of the proof is quite large. In our case, it's like, 200 some K. Now, if I'm running some proof on some machine on the internet and I want to send that proof to someone else on the internet, it's like pretty small, no big deal. The verifier is really fast. But if I want to use it for a blockchain application, you're not going to put 200K on Ethereum in a reasonable fashion, right? So the question then becomes, how do you do that? And what we decided to do is basically build a verifier for our Stark-based proof system that runs inside of a Groth16-based proof system. And so since we already had support for recursion, we were able to build a verifier circuit for the Stark-based system. And then by running the verifier for the Stark system in this Groth16 proof system, we can produce a Groth16 proof. Those have a fairly low gas cost on Ethereum, relatively anyway. 300,000 gas, and they're quite small, a few K. So posting those to the chain becomes a much more reasonable thing to do. Now, one thing we are working toward, near term is also having mechanisms for reducing that cost even further via the use of recursion to do aggregation of multiple proofs into a single on-chain verify. So that's something that is in the works. But right now we're really very heavily focused on really getting this 1.0 version out, which we're very excited about. That verifier for that will be live on mainnet very soon. And as I mentioned earlier in the call, we are ready to stand behind the security of the system for end-to-end use cases, for putting real money behind, for bridging of large things and stuff like that. So
what makes the RISC0 zkVM 1.0? What makes you confident that it is now ready to be called a 1.0 system?
We have been working on the underlying system for multiple years now. I started working on the initial prototypes even before we incorporated. And we have very much stabilized the RISC-V circuit itself. We've been making very minor changes to it for quite a while. We do have a sort of a 2.0 version that is in more flux, but we've stabilized it all. We've gone through extensive audits, reviews by partners over the course of many months. Similarly for the recursion circuit, which is the other sort of core circuit. And actually a lot of the recent development work has mostly been on sort of secondary things, not the sort of core functionality, additional performance, better support for sort of these precompiles or accelerators, higher level libraries like Steel that let you make it easier to talk about Ethereum state history. And I come from a lot of background of computer security. Many of my companies have been in the sort of area, and I also just have been interested in been involved in cryptography and computer security at an extracurricular level for quite some time. And so I think in that regard we have a very I think we're quite conservative in terms of when we say something is ready for production use case. I think we take a very conservative stance on that. And I think we really wanted to be ready for it. I personally feel quite confident at this point. So it's really just a matter of the stability and the third-party validation and a lot of internal looking and double checking and triple checking and so on.
I mean, the company is called RISC0, so you got to live up to the name.
Exactly.
Yeah.
It's an excellent pun. That was meant to be a working name for the company, but too many people liked it, so we ended up keeping it.
Yeah. I was going to say, it looks like you guys recently took a test by the Trail of Bits folks called their RECT test.
Yes.
And they ran your code through a series of checks that seem fairly important or often like code smells, things that might indicate other things going wrong. And one thing that I think is often difficult around specifically projects that are sort of breaking new ground in cryptographic engineering is that there's the question of, well, the auditors can be good, but this is a sort of like different ground from like an auditing a system that already exists before. And so with these zkVMs, it's really like, you're auditing something that has not existed before. And I'm curious how you guys think about approaching your work from a secure perspective, and like, to what degree can you work with auditors and help them figure out exactly how best to approach the understanding of their systems, and so that we can maybe understand how better to audit like novel systems that really are only just starting to come into existence.
So I think one of the things is some level of diversity of different people looking at it. We actually have some parts of it that we've had looked at by multiple third parties. Part of it is ways to figure out tooling to help verify certain properties. We've actually done one of our long-term goals, which we are not actually at there yet, but which in some sense played into our choice of RISC-V, is an interest in potentially formal verification at some point, right? So we've actually started some early work in terms of formally verifying the verifier, formally verifying the actual RISC-V circuit itself. So at least portions of it have actually been checked by sort of internal tooling. What we like to see when we get an audit done is some findings, right? Because if they found nothing, then you got to ask yourself, are they looking really, really hard? I think that we were generally, happy to discover that our auditors found some things, but nothing that was like major, or like most of the cases were not like really soundness bugs, but you're looking for audits that show very strong evidence that they're poking at the right things and there's a deeper understanding of the system. I mean, then, lots and lots of back and forth, right? This is not like a black box process, right? If our auditors want to know something about how something works, we're very happy to go into whatever level of detail to help them look through things more carefully. And I think a lot of it's also just an internal culture. We have a lot of people who have a very strong interest in, code. We have a very strong code review culture internally. People double, triple check things. We spent some time having people go back and re-examine code, internal developers, right, as part of the process, right? So I think it's really, you've got to sort of have this defense in depth where you're taking a lot of different approaches to trying to make sure that you've got something good, and also just locking down and not changing code unless there's absolutely necessary, right? So you just start to slow down your for the security critical parts of it, at least. Yeah.
And even if I don't wish that this would happen in the future, should there be a soundness bug in your proving scheme and you're live with a proving network, would you be able to share with us how this proving network would work, its upgradability would function?
Yep.
What would actually happen should there be a critical bug? What are the training wheels? Is it like a multi-sig like most systems in production out there? Or are you already like considering different approaches to address these dangerous incidents?
Yeah, so absolutely. So we have a bug bounty program that we're building. So the hope would be that through a good bug bounty program, we can find out about things before they are out there in the wild. But of course, nothing's ever perfect. We with regard to the verifiers on chain, we basically have a mechanism which it's an opt-in mechanism because people may want to. There's basically sort of three levels of sort of opting in. Well, one of them is you can just take the verifier contract as it exists in version X, and you can just call that contract directly. And then it's unalterable, that no one else can affect it. And if there's a bug in it, then it's up to your protocol to have some kind of incident response plan, right? Second sort of level is that there's a wrapper that we signing keys for that's like a stop wrapper, right? So that basically, if we discover a critical vulnerability, we can cause the verifier to stop so that no more transactions can be proven. So if there's a soundness issue, right? And then there's sort of the one where there's actually support for upgradability as well, so that as we continue to put out new versions, there will be a process by which we make sure the version is production ready and we support an upgrade. And if you trust us to be good stewards of that upgrading process, you can point at that contract. Even that one, I believe I think there's a time lock on that one, so that like from the time an upgrade is scheduled, you have some opt-out period or something. I can't quite remember. One of our other security engineers did the sort of high-level design of most of those. But yeah, that's so we're already thinking about these sort of production kinds of concerns with regard to that, and we will have those as part of the sort of first verifier on chain for this release.
And now there's this question that I always want to ask RISC0 engineers in regards to the feasibility of basically proving the behavior of an off-chain program. I always foresee a future where there's that nuclear power plant that's running a software for, I don't know, its cooling systems or its centrifuge, you name it, I don't know. And that software generates a trace. Is there a way to actually prove that execution trace and make sure that the behavior of the systems hasn't been tampered, and pretty much use a general purpose proving system to toughen civil infrastructure?
Yeah, I mean, absolutely. And, we are actually, so I think if you look at it right now, the place where ZKPs are there's a huge amount of immediate interest and economic value are a lot of these sorts of blockchain use cases, like the sort of scaling use cases and the privacy use cases. But we fundamentally believe that ZK is a very general purpose technology, and we have been in discussions with some non-blockchain related commercial use cases for this, of which I don't really know that I can speak to in any detail. But effectively, if you think about it, any type of system where you want to be really sure that what you intended to execute was what you actually executed, ZK is a great solution for. Even, things like banking applications, or basically any place where people are using HSMs or, high security sort of hardened computational systems, ZKP is a potential way to solve that problem. I think that the thing that's great about ZKPs is that they are almost every other way of doing computing in a verifiable way. There's ZKPs, assuming, if you imagine that we get to the point of having a formally verified correct verifier, and we have a formally correct, we formally prove that the underlying mathematical assumptions of the proof system are in fact correct, and we formally verify that the RISC-V execution does in fact translate to the circuit exactly, you could have extraordinarily strong assurances that what you ran is exactly what you intended to run, and no amount of like hacking or physical manipulation of the system, or it becomes really truly almost like an unhackable computer. If you compile C++ code down to RISC-V, then you still might have a null pointer problem. But which is, by the way, part of the reason we chose Rust. We actually do currently support C++, for example, but the build process is a little more annoying. There's not as good tooling for that. But most importantly, if you're going to be focused on a secure system, the sort of memory issues that C++ has are a little more concerning, right? So we've really focused on the Rust toolchain. Sorry, I'm going off on tangents here, but
So one of the original things that would sort of stand out in the RISC0 architecture is that, as far as I understand, the thing that you can't allow in the compilation step is non-deterministic compilation. That is, if there's a step that could compile in several different ways, then you can't compile that code into a RISC-V emulated circuit. I guess the first question is, are there other constraints on what can and cannot be allowed into sort of the RISC-V emulation? And then the second, I think, is I'm curious, it seems like you guys are targeting to support basically all of the ecosystem crates that you possibly can. What crates have been sort of an interesting story in terms of like the integration process?
One of the wonderful things about the RISC-V architecture in general is that the specification is extremely tight. There is no sort of implementation defined or undefined behavior in the RISC-V spec. And in fact, actually, there are some places where like memory ordering is allowed to have certain properties, but if you say it's a serially ordered system like us, then really pretty much everything is fully specified, right down to extreme level of precision, which is great. In terms of actually compiling real crates, what's interesting is there's a couple of different, so clearly, so most of the problems that we've run into really come down to crates that require specialized platform support where there's like gets down into assembly code or things like that, right? In a lot of cases, there's crates where maybe they only support ARM or an x86 and they just don't support RISC-V, right? We've also run into a number of cases where there's issues with, we are a 32-bit target. There are some things that don't really like the 32-bit targets particularly much. Issues with atomics, although I think most of those have been fixed. So the way the RISC-V standard works is there's a core RISC-V standard, which is, in our case, RV32I. And then there's extensions, which we include the M extension, which adds multiplication and division, which aren't even in the core. And there's additional extensions, like, for example, for atomic memory operations or floating point or whatever, right? Most of which we don't support. So there's a couple of places where like there was support for like RISC-V assembly, but they use those extensions. And so we needed to like work through those. We are currently working on some new work that will help us. So we're, in some sense, for many of those cases, we have either patches or we've gotten patches upstream. The fact that we're now an actual valid Rust target, so we've actually gotten our target upstreamed, has been good for us to be able to help patch some of these more unusual kinds of crates. But we're also working on some fundamental techniques to improve our general compatibility for the next rev of our circuit, which will allow, I think, a much wider set of crates to run out of the box. Oh, of course, actually, the biggest one, I forgot to mention, was probably more relevant than all of these, are things where there's assumptions of the ability to access certain operating system behavior, which is non-existent in the zkVM, right? You can't really open up an HTTP socket and talk to someone on the internet through the zkVM currently. Although there is interesting ideas about how one might make such a system work, but not in the 1.0 version. So.
Gotcha. And a lot of it would generally look like taking advantage of resources on the operating system that don't necessarily exist in the zkVM circuit.
And there's an interesting question about, as you look at, like, it's instructive to sort of say, just walk through the POSIX spec and look at, like, what would that mean inside of a zkVM, right? And some of the things actually are sensible. If you look at like file IO, one could imagine that the zkVM would, when executed, have some Merkleized file system root pointer, and when it was done running, it would have what is the updated file system root pointer, and you could build some sort of file system support that would run inside the zkVM. And then someone could open it, see passwd and see what's in there, right? Some of the things make less sense. It's interesting, like lots of things like time or, I mentioned earlier, randomness are particularly interesting because they tend to relate to how the zkVM is being used. So I think this is a continual ongoing thing. And I think we're really well suited as a company to help move those types of things forward. We're already doing internal research on some of these. So look for new exciting functionality in the future. So.
Nice. You mentioned briefly that there's at least consideration in how you would open provision TLS socket or basically talk across a network. I'm familiar with a couple of ideas about how you might conceivably do that, but one of them is TLS Notary that's being developed by the Privacy Scaling and Ethereum Foundation. Was that the particular scheme you're referring to?
I think in many of these cases, the way we're kind of considering it is in terms of some sort of a policy. What we want to do is we want to make the environment within the zkVM look as similar to a normal computing environment as possible. But when you do that, there's sort of like decisions that have to be made about what you want to do in certain cases. In many cases, the right answer is when you try to open a network connection, it should fail. In some cases, the right answer might be, well, actually, we're going to use TLS Notary. I think another example would be, how should time work? Is time something that is controlled by the chain and you want to go with whatever that says? Is time whatever the local time on the person running the prover says? Is time something you shouldn't be allowed to access, and anyone who asks for the time should cause termination of the program, right? So I think like one way to look at it is that there are anything that is outside of normal computation, anything that involves talking to the operating system, it's important for the end user to be able to understand what their intent is so that they don't accidentally invoke behavior that they didn't intend to, because these are all for security critical sort of use cases in many of these cases. This is a little more far afield, I would say. By and large, most of the work people want to do right now is really very much on the pure computational side. But I do anticipate that these sorts of, in the long term, like I said, I think making zk as accessible and similar to normal computing as possible is one of our goals.
In the same vein, it seems like one of your recent projects recently announced a project called Steel,
Yes.
which also runs in the direction of allowing developers to basically treat the Ethereum blockchain as a system resource and query for on-chain historical artifacts. Could you tell me a little bit more about the development of that and sort of like where it is, like how that came about?
Yeah, absolutely. So, I mean, I think if you, when we looked at a lot of use cases, one of the things that became clear across multiple different partners and, customers and people we're working with, as well as some of our own internal development work, is that this notion of doing a sort of Merkle proof of the fact that something is in sort of Ethereum state history is a common pattern that's done over and over again. I want to show that as a block such and such, some state of some account was something. And it's just a lot of boilerplate code that was like to go grab the block, go find the thing, find the Merkle path through it, produce the Merkle path, pass that in as an input to the zkVM, verify the correctness of it. And really what you really want to do is you want to just say, I just want to call a view function on this contract and see what it returns, right? But in order to do that, this orchestration has to be done by something somewhere. And so there's this question arose of how do we make that as transparent to the end user, or the programmer, really? How do we make that as transparent to the developer as we can? And so that was where the idea for Steel was. And, it turns out that like Rust is a great language, but particularly delightful is its sort of macro system. So we were able to actually sort of do things like put in the Solidity code that defined the, what the set of view calls were and so on directly in the interface, if you will, into, just a macro in Rust, and use that to then generate all of the sort of things downstream. So, the idea that we have a number of different people who are now sort of using some of this Steel work for their use cases. But, I think this is the kind of example of, I mentioned earlier that there's sort of really three core things that we're doing. One of them being the sort of actual core zkVM itself, which we, are continuing to work on in terms of capabilities, compatibility, performance, all of those sort of core functional things. Then there's this proving network sort of use case, which is how do you actually deploy this? Who runs the proving? How do you decentralize that? Like sort of Bonsai is where we're at right now with that, but we're working on a number of new things in that direction. And then the last one is this sort of set of really tooling just to make all of these things easier. And there's a lot of exciting things to be done on that. Steel being one of them. Zeth is sort of one of these projects in that direction. One of the other things to note, by the way, I talked a lot about sort of our verifier going to mainnet. We have a very cross-chain sort of view. So we actually intend to put the verifier live, not just on Ethereum, but on a number of other networks, including both EVM and non-EVM based chains. One of our sort of, our tagline is sort of prove anything, verify anywhere. And so we really are intending to go forward with this wide number of different ecosystems.
I would like us to dive deeper into the role of RISC0 as in the infrastructure landscape. So we like to see it as some kind of proof of correctness as a service. So you can basically summon the proving network to extend the safety guarantees of an existing system, like maybe an optimistic rollup, or to make it cheaper to run while offering like better security guarantees to something.
Yeah, absolutely. I mean, I think we look at sort of there's sort of really a couple different use cases that we see that are common. One of them is the roll up or the L2 kind of use case. And in that case, you have some system that is running and produces new blocks or new state updates on a regular basis. And what you really want is a way to prove that the new state update is valid given the old state update and maybe what's in DA or what have you. And it varies somewhat based on the particular use case and the design of the protocol. So that's sort of one kind of use case. And we actually see that as like, that's sort of the more high volume in terms of proof volume sort of use case currently. And I think that also applies to some extent to sort of optimistic systems where maybe the ZK isn't invoked on every block, but if there's a dispute, there's lots of ways to use ZK to rapidly resolve the dispute without having to have as many back and forth operations on chain, which can reduce the dispute window. So both sort of the use of ZK to improve optimistic protocols and the use of ZK to do ZK validity sorts of use cases is sort of one half. And then the other sort of half of the market we see, and we have a number of people working in this side as well, is really what we call sort of the ZK coprocessor direction. This model is different. Most of the state, for example, might live directly on your chain, whether it's an L1 or an L2. And you're really just sort of offloading the compute. And so the idea here would be you would generate a proof on demand when you needed to prove some particular thing. So like a good example might be a governance use case, right? You're going to do a vote and you're going to do all your vote, accounting, tabulation inside of a zk proof off chain. And it's really fundamentally a cost reduction in terms of the gas, because the cost of doing the proving is vastly cheaper than the gas cost, especially if you look at places where the gas cost is high, like Ethereum L1. And so that's a sort of another sort of direction that we're seeing in terms of DeFi use cases or gaming use cases or governance use cases or these kinds of things, where it's really more about moving the compute off chain rather than having sort of this separate stateful machine that runs and has, regular updates.
All right. I think that's pretty much it on my end. I might have actually, or maybe Tori want to add something.
Oh, well, there's definitely the most important thing that we need to talk about in this call, and that's recently a crucial bit of research was performed and announced on the RISC0 blog, and that was whether or not we can run Doom inside of a prover circuit at relatively feasible times. And initially, we came up against an issue that we talked about earlier in the call, and that's that Doom assumes basic system resources. But it seems like you guys found pure Doom, which does not rely on system resources. And so I would love to hear a little bit more about the story of how close are we to me playing Doom and then proving that I've been playing Doom this whole time and not some other game. And that's really the main thing I'm here for in zk, is whether or not if we can run Doom, then the rest is history.
Yeah, exactly. In my opinion, since the original conception of this idea of putting a general purpose processor into zk, Doom was on our minds. Really, it just took the engineering work to get continuations and parallelization and all of this work to get something where we were actually, and just also, just dotting I's and crossing T's, and of course pure Doom to get us over that line. The reality was, in some sense, we thought of it very early on. We knew we were very far from it. We worked on all the intermediate steps, and then hadn't thought about it in a long time. And I can't remember the context in which, again, a couple of us were sitting around and we're like, hey, wait, we should be at the point where we can run zkDOOM now, right? And so Parker, who is one of the people who works here, set out to sort of go solve that, mostly as just like kind of a fun thing to do in his spare time. And obviously it worked great and is a delight. I think in some ways, it is a milestone in zk in some sense, because it's really showing that it isn't just for some very specialized use cases. It really is general purpose. And I actually think one of the things that's really interesting is that something I've realized that zk allows is that zk allows you to trust the client, which is something that has never existed in computing history. So, in some sense, we already understand from a blockchain use case, well, the real trick is how do you execute something in an environment where you don't trust all the people executing it, right? And a lot of this execution scaling all involves running something on a non-trusted machine, but being able to trust the result. That's what gives us the power of all of this sort of zk scaling. But another way to look at it is, if you look at a client-server architecture, I can now actually trust the client. And that opens up a wide range of interesting possibilities. Now, the reality is in our current prover, you absolutely can run on your own laptop. We actually don't take that much memory. We're pretty performant. We run on most consumer GPUs, but it's still not easy. So one of the things, we are doing some research into making sort of client-side proving faster and better, because I do think there are a lot of these use cases, but not only including, being able to run Doom and verify that to your friends. Make sure that your high score is truly well earned. But yeah. I kind of have a want to do a project just for fun at some point, which is a 6502 emulator, so that you can do zk proofs of old like Nintendo games or things like that. Of course, now the thing is you still can do tool assisted stuff, because we can't really prove that the keyboard's connected to a live keyboard. You know what I mean? But at least the speedrunning world could have zk tasks where you can show that there is in fact a way to get Mario from point A to point B in this many frames. And I'm not going to tell you what it is, but there is a way to do it.
Yeah, that's truly inspirational, where I can task to say that it's possible without Twitch streaming it, which is, I think, the future that we're all here for.
Yes.
Speaking of those use cases, I just remembered about ETH Denver 2023 hackathon winner, which was ZK proof of exploit. I'll be very curious to see you guys using that solution and set up a huge bounty for whoever manages to prove that they're able to break your systems.
We have actually talked about that because it actually makes sense, right? I mean, I think that the proof of exploit is really a fascinating thing. Actually, we've also had people who are interested in formal methods work. What's interesting is you can make a formal proof of some mathematical statement, and you can zk prove that you know a proof of some theorem without revealing what the what the proof is. Someone should do that with the Fermat's last theorem, although that I guess it was eventually proven the old-fashioned way. But
there's only so much that can be designed out of that stack you guys are building, and I will of course leave all the relevant resources in the description below, and invite anyone to ask questions in the comment section as well. I wanted to say thank you, Jeremy, for joining us today on the show and telling us about all the amazing things you guys at RISC0 are working on. And thank you, Thor, as well, for being our co-host, and thanking our listeners for tuning in. Wishing everyone a wonderful week, and I'll see you very soon.
Thank you. It was really fun to be on the show.
Thanks.